All right, next speaker, Dr. Kaiyu Guan, Blue Water's Associate Professor in Eco-Hydrology and Remote Sensing, founding director of the Agro-Ecosystem Sustainability Center at the University of Illinois Champaign-Urbana. I'm eating Cheetos talking on the radio. Look at this guy. I saw on a website, I was like, look, I was so impressed with his bio. I looked at his website, I was just did a little search, and there was one website that says, Kaiyu Guan is an innovator. I thought that was, especially in the field of food production and changing environments, very impressive. Has published more than 140 papers in leading scientific journals, PhD at Princeton, postdoc fellow at Stanford before joining U of I in 2016. Also, along with NREC, federal grants from NASA, the National Science Foundation, the Department of Energy, and the U.S. Department of Agriculture. Please welcome Dr. Kaiyu Guan.
This is I've been here for many times, so it's great to see a lot of the old friends every year. And then so thanks Julia and Shani to invite me this year again. I decided to talk about cover crop because this is the work that we've been working on with different source of support, but NREC play a critical role here. And then so I also want to acknowledge some of the major contributors, including my student, Ziqi, sitting here. She's a modeler, doing a lot of modeling work that I'm going to talk about. We also have Shen Chu, scientists that are also doing a lot of remote sensing work. We have been working very extensively with researchers that has been funded by NREC that doing a lot of critical trial work, including Andrew's work, Marianne's work. We've been working with Dan Schiffer, really working with farmers to go to collaborate with them, go to their sites, to do some samples, fly over their sites, take measurements. And then so really appreciate this is a great community and a great group effort. And so with that, I'm gonna talk about three aspects. And then so the first one, I'm gonna talk some of the sensing part. So we use some of the remote sensing tools to better understand cover crop. And then so sensing is important, but sensing does not really penetrate into the soil. So if you want to know the implications of cover crop for the environmental benefit or even the crop yield implications, so we need to do some modelings. And then last but not least, I think all of this work ultimately needs to anchor on the management practice. Can we generate some useful insights for some farmers, for our farmer communities? So first, this is a very interesting work we just published this year. What we do is we use a lot of the public satellite data that NASA launched and then try to basically scan the land to see which land has cover crop or not. And then so what we can find is in the past 20 years, if you chunk two periods, the first 10 year and the second 10 year, you actually can see the cover crop has been pretty significantly increased nationwide. And then some of the states, including our states, if you focus on Illinois, about the first 10 year, our average is probably just around 2%. But in most recently, our average cover crop adoption becomes 7%. So which is a pretty impressive increase. And this trend is continuing improving. At the whole national level, we do see that the first 10 year increase is very stagnant, but then the past 10 years, we start to see a sharp increase. And then some of these has been, we believe, related to some of the increase of the government conservation fundings that come into our farmer community. But more importantly, I also believe farmer has been better aware of the benefit of cover crop, which is why we continue doing the NREC work that tell farmers, what's the benefit of cover crop. But at the same time, I'm gonna talk about something that cover crop may actually leads to some issues. But the conclusion that I want to really say is cover crop bring benefits, but it needs to be managed. So we need to, if scientists could help farmers to better manage the cover crop such that you minimize its negative impact, but get the benefit of that, that's always the best situation. So actually this work get quite a bit of press. We reported by some of the academic organizations, medians, but also being covered by Washington Post, that they actually excited about cover crop adoption is increasing nationwide, and why that's a good news. And then so pretty good, I think, the work that has got some national press. But the remote sensing work is only one part. Essentially you scan the land, you only see, we try to get a very simple answer whether that field has cover crop or not. But what's more important, as you already aware, is how will your cover crop grow? How much, for example, nitrogen has been uptaken by cover crop? What's the biomass of the cover crop? And then so because of these implications, we actually did some effort that collaborating with our farmer collaborators. So these are the sites, the triangle are the sites that we have our farmer collaborators actually allow us to sample their field at their locations, and then allow us to fly a university-owned sensor in the airplane that take hyperspectral sensors. So what we end up having is a particular field. We should be able to tell for the cover crop the detailed information about the cover crop in terms of the biomass, nitrogen concentration, and the carbon and the nitrogen in the biomass, all these informations. And then so we actually shared these results with Dan Schiffer, as well as a lot of the farmers that actually participate in our program. We share this information back to them, and then they actually find it's quite interesting to know how their cover crop has grown. So in other words, that if you're still interested in doing some of this work, this is for free. We just reach us, and then we may find a time to use our sensors to look at your field and then give an assessment report. But these are the information that we actually able to tell is how will your cover crop grow, how much nitrogen you actually have been uptaken from the soil, or how will your biomass look like. And then so once you get these measurements, we start to do modeling. And so my group does not do a lot of the trials. We are primarily modelers and remote sensing scientists. But I understand deeply about if you want to use any model, you have to really validate your model. You have to tell people how will your model perform, because otherwise you don't have that foundation to conduct your research. And then so with that in mind, this is why we extensively working with scientists who are conducting the trial experiments. So we previously we worked with Lowell, we previously worked with Andrew and Marian. So they have used their previous time and the investment from NREC, have collected a lot of the trials, conducted a lot of experiments about cover crop. And these data has been archived there. They published the paper, but we actually take their work, collaborating with them, take their data and start to understand, okay, with these as ground truths, can we use our model to reproduce these ground truths and patterns? And then so we have done a lot of the detailed validation of the work. So in particularly, we're gonna report some of the effort that we've done regarding this effort. So one aspect that we have done, these are some of the sites that we have a long-term monitoring of the cover crop trials, primarily done by Maria and Villameo group. And then so they actually spread out over the whole state. And so what you see here are the locations of the different states, as well as the rainfall and temperature distribution of the state. And then we also choose some of the sites, because in this study, what we want to understand is some of the key questions related to cover crop itself. Can we model cover crop biomass? But then what's also very interesting, or sometimes more interesting question is, if you grow cover crop, what's the implication of your cover crop to your crop yield, to your cash crop yield? And then that's a very important question. And then another layer of question a lot of you may be interested in is, we all talk about cover crops' potential benefits for soil carbon. And how much exactly is that? Could you have a way to quantify these impacts? And then so what we've done is we use these data set that has been collected by other researchers through NREC project primarily, and then use these data to validate our model first, and then try to use the validated model to generate some insights. And so, for example, what we did here, there's data for cover crop trials, but we also find multiple sites that has either a long-term soil carbon data record, as well as some paired sites of cover crop experiments, but paired with soil samples too. So these are rich level of data, but I think for some of you who hear the talk, of this morning, you know that a lot of groups are collecting more data, so we actually want to collaborate with them too. I know Andrew's group is collecting a lot of extra data, so very excited, more data is coming. In terms of a model, this is a basic setup. I don't want to bore you for too much, but essentially I want to give you a general idea of what we are exactly doing for model the system. So essentially, it's all computer code leaving the computers, and we use a lot of the supercomputers in the NCSA. But essentially, you can envision in the computing world, we have these codes basically try to mimic crop growth at certain time. It's like a parallel to universe, but you try to set up the crop, you let the crop grow, you try to model how crop interact with the environment in terms of the soil type, in terms of the sunshine, rainfall, temperature, all these variables. You try to model that, and then you let the crop dynamically grow to do photosynthesis to generate biomass, but it's all virtually in the computer. And then you also model the soil processes. So once you have the crop grow, you have the soil processes. The soil processes including the soil water. You want to model how water flow in the soil. You also want to model the biogeochemistry. In other words, you want to model nitrogen cycles, carbon cycles inside the soil too. And then the models that we also use actually model oxygen stress and pH values. So all of this has been simulated. Now the question is, you're going to ask me like, hey, it's cool, but then how do you know your model is doing the right job? And that's a question that I frequently got. And then, so this is why when we are using the model, we're looking at two things. One is whether the model actually has the necessary processes that we have learned in the textbook. So this is one aspect. But the other aspect would be even easier to know is, could your model reproduce the reality? Could your model reproduce the observation? And then so we use a model that's very sophisticated in the process. I would say that we use the textbook type of the knowledge. You can actually see that in our model. So it's called EcoSys. But then we also use EcoSys, try to simulate at these sites in the computing world to see whether the result could match the observation. And this is what you see, and this is a published paper by Ziqi in Field Crop Research last year, 2 years ago. So first, we check whether the model could capture crop yield. And this is one of the results that it's actually coming from the trials across the state done by Dr. Marian Villamail's group. So you actually see that our yield can well simulate it with all these, with the corn, and then with different the experiment. And the other aspect we're also very interested in knowing is biomass of cover crop. So these trials also take biomass of cover crop measurements. And so you will see that we largely also aligned with the biomass measure, simulation. It's lower, the performance is slightly lower than the cash crop yield. Okay, but still, the R-square is pretty reasonable. So we actually start to take these models to do a little bit more validation. And the next slide you will see is we also validated the result that we have related to the soil carbon. So, the top one plot that you see is the the longest soil carbon measurements in the US from Morrow plot, which is an experimental site in our university. And so you will see that Morrow plot shows the soil carbon, this is a 100-year record. Morrow plot showed the carbon in the first 60 years, it's really decreasing, and later, more recent 16 years, it's more pretty stagnant. And then so we start to see, if we use realistic weather information, we know the rotation pattern of the crop. We even know the crop yield of the harvested from these sites. And then so can we use all this information, bring together into a model, and try to see whether we could simulate the soil carbon dynamics in the state, in that particular plot. And then the short answer is yes, we did a pretty decent job that you will see our simulation can well match the result. So our simulation is this continuous wiggles. And then the measurements is only the dotted measurements, because measurements is usually not continuously spread out. So this is one pretty good news. And then the other good news is we also have some of the measurements that has the cover crop. So without CC means without cover crop, that plots, and with CC means with cover crop. So we actually can see that in terms of the response of the cover crop to soil carbon, we actually can also generate reasonable response of that. And so this work is recently published by Ziqi in global change biology. Very excited about this new work. So this is some of the validation effort that we believe can provide some good confidence of our result. And of course, more actual data will always be more helpful. So we are welcoming academic collaborators to see whether you have actual data for us to continue use and then look at the model performance and whether they match the observation. But these are also sort of the foundation. It builds the foundation for us to believe our model actually has some good capability to mimic the reality. I use that word, mimic the reality. So once you have this validation done, then the next question is really about, let's use the model to generate some insights. And so what kind of the insights we want to generate? These are some of the insights that actually has both observations response, because researchers has done this in trials, but also we could use models to see whether our model actually can reproduce this response. So one thing that we look at is the impact of the cover crop on corn soybean yield. And then so long story short, in this graph, what we are seeing is that when you have cover crop, no CC means no cover crop, and then ryegrass before corn means the ryegrass is a cover crop before cash crop corn, and then hairy veg before corn. And then so what you see, the dots are the observation. So this is from Dr. Villameo's group's research result, and then the bar is our simulation. So what we try to tell the story, interpreting the result is, we see that from the observation and then model result, they're all consistent. What they are saying is, if you don't grow any cover crop, your corn yield in that particular site is this number. And then if you grow ryegrass, you actually tend to reduce or lose some of the corn yield. And then if you grow hairy veg before corn, you don't have much loss in the yield. And then remember, these are the data somewhere like 10 plus years ago. So the yield number is actually not really well. So we actually, but I think this actually helps out, the conclusion still holds is why we are seeing this type of pattern. The reason that we see some of these patterns is from the modeling world, we can find the ryegrass before corn is actually has some impact on the cash crop. And then so the major reason is when you grow the ryegrass and then you are not terminating the crop in time, and then the crop essentially, the cover crop essentially sort of also take resources of water, take inorganic nitrogen in the soil, so they almost become a competitor of your cash crop. So you do have these competitor situations happening when you grow non-legume crop before corn. And then we have seen some of this, farmers also talk about this experience. If you grow ryegrass or cereal rye before corn, to a certain extent, you may expect a small yield loss unless you really properly manage it. And we're going to talk about that management later. But it's actually has been shown in both observation and models, and then anecdotes-wise, a lot of farmers actually also realize this may be an issue. So, but then if you grow hairy veg, the legume cover crop before corn, you see much less yield penalty, which is also confirmed by the observation, and then so some of the major reason is really because the hairy veg is a legume crop, so they are less competing with cash crop in the summer, mostly because legume crop doesn't really need much of the soil inorganic nitrogen. And then so similar thing, so corn, you see on the left side, you see corn has more impact, but soybean has a slightly less impact. So in other words, that if you grow cover crop followed by soybean, you don't see huge impact. But again, I would say is these are the modeling effort sort of corroborating with the observation. As we get more observation coming, we can continue doing this effort and have better understanding about what's going on. So this is very critical. It's not an entirely settled conclusion, but we are glad that we can actually capture historical pattern using our model. But then as this study needs to be conducted more, because we want to use the current varieties, the current management farmers are using, and see whether these conclusions still apply. But general principle still holds. This is about the termination date. I mentioned termination, management of cover crop matters a lot. So you want to terminate the cover crop sort of with some lead time, because especially for the cereal right before corn, you want to terminate the cover crop sort of early enough. The reason is pretty obvious, as I mentioned before. If you terminate the cover crop too late, true, you can let cover crop develop more biomass, but you also run into a potential risk of cover crop take too much of the water and the soil inorganic nitrogen before you plant the cash crop. And then so you don't want to have a situation that cover crop become a competitor of your cash crop. And then to a certain extent, a lot of the yield loss that we see from corn yield loss, when you grow cereal right before corn, the situation is mostly because your cover crop become a competitor. So they take very, very valuable resources of water and then inorganic nitrogen in the spring, such that the cash crop actually feel not enough nitrogen or water when they started. And then so this is a conclusion that pretty obvious that if you don't have cover crop, this is the yield, versus you start to terminate cover crop 1 day before the planting, 2 weeks before the planting, and then 4 weeks before the planting. So in other words, that if you terminate 4 weeks before the planting, you actually your corn yield is actually not lost that much compared with you just planting 1 day before you planted corn. And then the next graph is showing that the cover crop termination date before corn, again, the cover crop biomass. Basically, it's a compromise, because if you let cover crop stay in the field a longer time, obviously cover crop can grow larger. But this also creates a trade-off that they grow larger, they may take more resources in the spring, which may make cover crop become a competitor of your cash crop. So I think these are like pretty straightforward to understand. So the tricky part is how do we manage that? I think we're gonna talk a little bit about that. How do we manage that? Before we go to that step, we also want to talk about carbon, soil carbon. I know that Andrew and others already spent a lot of time to talk about it, but I would like to talk about carbon in a relatively, in a more kind of naive way to help you conceptually understand the carbon situation. So when we try to say, can we build soil carbon? If you think about soil carbon as a bank, essentially what happens is it's a bank, then it's about income and your spending. So how much carbon goes into your soil minus how much carbon leaving the system, leaving the soil. What's the net change in the long term is the soil the change of the soil organic carbon. So in other words, if you get carbon in but not sufficiently offset your carbon going out, then the system is losing carbon, losing soil carbon. Inversely, if you get more carbon into the system and you do not use it as much as before, so then it creates a net income of the carbon to the system. And then to a certain extent, this is as simple as that. Now, so then the next immediate question is, you're gonna ask me, what's the carbon goes into the system and what's the carbon goes out? If we have the ability to quantify what's carbon goes in, what's carbon goes out, the net change is basically the carbon, the soil carbon change in the long term. I keep saying in the long term because soil carbon change is a pretty slow process. You have to wait. But the mass balance, what I just described is the basic mass balance. That does not change. You're always going to have the situation that you get the carbon in minus the carbon goes out the system. That net change is what you left. So then thinking about what are the terms that goes into the system. What are the terms going into the system of the carbon? The major one, the most important one, is the photosynthesis. So if you grow either corn or soybean cover crop, if you grow cover crop with much larger biomass, it basically means it generates more photosynthesis. You're actually gonna help bring more carbon to the land. But then, before the carbon goes into the land, what's the carbon goes out? Thinking about the plants, think about crop. So if you get photosynthesis, you grow the biomass, but as a reality, also biomass, the crop actually use some of their own carbon as respiration. And then also for the crop, once you build the biomass, major part of the crop actually will become crop yield removed of the system. So you sort of only have the residual left on the ground. And then so these residual goes into the soil. These are the primary carbon input to the soil. What's the carbon going out? The carbon goes out primarily are the soil heterotrophic respiration, which is essentially the carbon that decomposed and then has been consumed by microbes. So these are the carbon left. There is some carbon left the system as erosion, and depends on where you are. We have some erosion here, but not huge because our land is relatively flat. And then so if you're thinking about carbon goes in and goes out, what I just described is helping you to better understand the general pattern of the soil carbon you can write even in this simple equation. The simple equation is change of the soil organic carbon in the soil equals the carbon goes in, that's the photosynthesis, minus the soil respiration, minus the plant respiration, and then grain yield is also carbon you remove out of the system. So if you have the ability to quantify all these three or all these four individual components on the right side, you should be able to know what's on the, the change in the soil organic carbon on the left side. And essentially, this is basically what model does. And then what model does is try to quantify these different individual components and then try to quantify, try to use observation and measurements to see, can we have a better quantification of soil can we have a better quantification of photosynthesis, or can we have better quantification of plant respiration, soil respiration, or grain yield? So this is, again, a graph from Ziqi's paper. I don't want to bore you into details, but essentially what I want to let you know is cover crop, it's actually going to increase soil carbon. I don't think people thought about this, but you're going to ask me, what's really going on? What's the major mechanism behind the cover crop bring the carbon to the system? It's primarily because cover crops biomass. So you have the biomass generated from photosynthesis, and then these biomass, you don't harvest them. You let them stay in the field, and these become the residual, mostly stay on the land. And then these type of the carbon are the major input to the soil system. Now, that's not entirely all the carbon of the biomass or the residual becomes soil carbon because there is a soil respiration. So in other words, that even you have the residual of your whole biomass initially as all the residual, but over the time, part of the carbon will become, be consumed by, microbes, and those carbon return back to the atmosphere. So you only get a certain part of your biomass left, and in the long term become soil carbon. And then so the reason that cover crop actually benefit from the soil carbon perspective is really through the cover crop bring the generating photosynthesis in the winter time, and then these residuals, these cover crop biomass stay on the land, stay on your field, and part of this biomass become the soil carbon in the long run. And as a result, these are coming from Ziqi's paper. Again, what you see is the cover crop biomass you grow is actually linearly correlated with the soil carbon benefit you generate in the long run. And then that's also not strange. If you follow my logic, what I just said is, if you bring more photosynthesis to the land, to the biomass, and then you let more biomass of the cover crop stay, you're actually gonna bring more carbon into the soil carbon pool in the long run. And then so that's not a difficult thing to think about. The second graph on the right, it basically means that the root-shoot ratio. So in other words, if your cover crop has more root biomass, you have more chance to get this biomass into the soil, and that's also obvious, because the root biomass they are already in the soil, while the background, the residual part, are not really in the soil. So the conversion efficiency will be different. And so that goes to the question that I want to talk a little bit about. Again, this is from Ziqi's paper. It's a little bit abstract, but what we are trying to say is this contour, the x-axis in the top part is really your planting date of your cover crop, and then the y-axis going this way is your termination date. And we use a very realistic example in Champaign County. And so in other words, and then the contour color refers to the biomass you generated. So darker color means you have more biomass generated. So what you expect to see, and it's consistent with our models, is if you grow cover crop earlier and terminate later, you're gonna generate more biomass, obviously, okay? Obviously. And this is what you see, is exactly what you're seeing here, is the highest biomass is going to be generated when you have the latest termination date. But remember, the trade-off here is if you want a cover crop to grow more, you want to gain more carbon benefit, but then you inevitably let cover crop grow too further, close to the planting date of your corn, such that cover crops start to become a competitor of your cash crop. So this is a trade-off that we always talk about. In other words, gaining more carbon versus you don't want a cover crop become a competitor of your cash crop. These are actually two competing interests. And so how you want to deal with that, I think, want to talk a little bit towards the end. Again, this is the very detailed process. Not really I want to talk about here, but if scientists or students interested, go to check the paper. We talk about how cover crop affect the yield, cash crop yield through multiple pathways. It's not just as simple as what I just described. It's actually pretty sophisticated. You can go into these processes. Again, same thing. For soil carbon impact for the cover crop impact for soil carbon, it again has multiple processes embedded, and then so we are trying to really understand the processes underneath. And again, it's too complicated. I don't want to use today's time. But last but not least, I want to use the model to really help envisioning what's the soil carbon benefit from cover crop. And then usually we talk about we grow 2-year cover crop and then start to stop. Or versus you grow 4-year cover crop, you stop. You versus 6-year of cover crop and then you stop. This goes to why we want to use a model. Because sometimes we joke with our farmer friends, usually farmer in their career lifetime, you can see 30 or 40 years of the harvesting time. But in the model, we can do 100-year simulation. If you more or less can make sure your model is realistic, you start to use your model to infer something. And I'm being cautious. I'm not trying to tell you that you just 100% trust model. But what I'm trying to say is, because model, you can run that much cheaply, and you can run with different scenarios. If the model has been validated and has its rigorousness, you can actually use that to infer some insights. That's all what I'm saying, okay? And so what I'm trying to play a scenario is a very interesting scenario. So I'm gonna see if I grow cover crop in my computer, that I just told you, the model that I used. I grow cover crop for 2 years and stop, versus I grow cover for 4 years and stop, and then 6 years and stop, and then more and more. What will be the situation? So what I see is, let's look at the situation of you don't grow cover crop, just corn soybean rotation system, versus you start to grow 2-year cover crop in these 2 years, and then you stop. What will be the soil carbon change? So what you see is the cumulative soil carbon change over the time. So you're gonna see when you grow the cover crop in the first 2 years, 2 or 3 years, you're actually gonna gain the peak because a lot of the biomass has been generated and then stay on the field. But then you have a very long tail decaying, and the decaying is really because the biomass generated, you also have the soil respiration generated. So at 100-year time frame, what you actually end up seeing is you keep decreasing. In 100 time frame, you only get around 1/3 of your initial highest carbon gain. And then this talks about somewhat of the durability of the carbon benefit you're gonna expect to see. Okay, I'm very close to end, but this graph shows more. Now it's only not 2 years, but you can start to talk about if I grow 4 years and stop, 6 years, 8 years, and 10 years, I stop. What will be the situation? You can actually see, you continue to increase your soil carbon benefit, but once you start to stop your cover crop adoption, your benefit gonna decay. You still get benefits, it's still positive, but you're gonna actually have a discount over the time. But this is sort of obvious, but then if you visualize this, you sort of see, okay, this is what's gonna happen in my soil carbon. Or what I'm saying is, this is gonna be a very slow process. So if you expect soil carbon help you for crop yield for your soil, it's true, but it will not happen over a year. We are talking about decadal benefits. So in other words, growing cover crop, you got to be patient, and then you got to be patient to see the impact. So with that, my talk haven't covered like cover crop impact for nutrient loss reduction, which is something what we are doing. We haven't covered about other aspects. Model always has its trade-off. Don't take it. Don't just sort of partially quote my words that model gonna solve everything. No, it's not. It's actually empirical data, trial experiments, paired with some modeling, can actually generate a lot of the very good insights. This is what I'm trying to say. Last but not least, I think the conclusion is we are increasing our cover crop adoption, but we still slow, we still low rate. Cover crop needs improved management. And then, some of the scientific reasons behind this, as well as I think soil carbon benefit for SOC is real, but how you perceive that, it's a dynamic process. Again, thanks to all the farmer collaborators, all my other collaborators, students, done all this work, researchers done all this work, but I really appreciate NREC's support. Thank you.